Hi, my name is Phillip Clendenin, and this is the fourth lab for Physics 2212 Section P covering circuits and capacitors. In this lab, we are going to be using a virtual program to run the lab, which I predict is going to remove some of the natural human error that we generally expect in a lab. In doing this, we are going to use primary physics topics, specifically the loop rule and the aspect of a steady state, which I will describe future in a minute. Using these energy conservation facets, we're going to predict the behavior of circuits in multiple directions, as well as use multimeters such as ammeters and voltmeters to measure the values of current differences. Amongst all of this, we will inspect the effects of capacitors and resistors, as well as their tendencies. Before describing what the loop rule is as well as the steady state, I just want to make sure we all understand what circuits and capacitors are. Put very simply, a circuit is just a loop that is electricity and charge can flow through in a certain direction, and these loops are almost always closed. While this may seem very basic, it is important to note that if the loop is not closed, there will be points in the circuit where there are no longer electrons or charge flowing through. From this lab, we expect all circuits to be closed. Continuing on to capacitors, for the sake of this lab and discussion, we are going to discuss resistors as well. We know these two things to have very different uses or effects in circuits. Capacitors, which are going to be a greater focus in this lab, are generally plates within a current flow or connected to such, and then because these two plates have opposite charges that are equal, a charge or potential difference builds up and stores over time within the room between the plates. While this charge or amount of charge determines how fast the potential difference is growing, the capacitor never takes away power or charge from the circuit. On the other hand, resistors, however, their primary role is to inhibit or limit the speed or efficiency of a circuit. They are measured in ohms, and although they impede the circuit flow, they do not halt it entirely. Back to the more specific topics, let me discuss the loop rule. In any closed circuit, which is what we're focusing on today, the sum of all potential differences created within the circuit must sum to zero. Similar to the potential means, or the means of how we sum all electric fields and magnetic fields by superposition, the potential difference or charge of each of the sections of the circuit can be calculated individually, and then we will all sum them to zero, which is helpful in terms of solving other problems. Continuing on to the steady state, rather than say it is a thing, it is better described as like a list of rules, or that a closed circuit in the steady state must follow. Because it is more of a state of a being rather than an effect, we describe it as aspects of a circuit. For a circuit in a steady state, the charges are moving in the conductor, the drift velocities are constant no matter the location, and finally the polarization is not dependent on time, but dependent on location or spatial orientation. Discussing the experiment aspect of this lab, we first are going to be using a series circuit of two 1.5 volt batteries where the two resistors and two ammeters as shown in the diagram. When we did this in the CCK, I predicted to be roughly around 0.02, and prior to discussing the validity of my prediction, this reading will be the same regardless of its orientation of the ammeter, or if it's forward or reverse as we were prompted to do in this experiment. However, if we were to replace our ammeter with a voltmeter, we would still have the same reading because the amount of resistance it puts off. However, our total voltage or change in voltage would be 3. Continuing on to the graph of potential versus position around the circuit, we have the completed portion of the graph in blue. Our reasoning or explanation for this is that when we look at the battery wires and resistors, we know that the batteries allow the potential to increase while the wires have very little effect, and then the resistors each lower their respective amount, with the 100 ohm resistor doing more. Moving on to the observation portions, when for the questions in relation to the light bulb and the charge, the first observation resulted in the bulb lighting up very fast, and then the second lit up very fast as well in a very similar fashion. These two were related to the capacitor charging and discharging respectively. In both of these scenarios, we see the current flowing quickly and then waning off to zero, and we also see that for the time to charge, the one with the lower resistance charges much faster and discharges faster as well. Finally, getting to the voltage versus time graph, we originally see a distribution of a graph that shows an exponential decay slowly going towards zero. However, when we do the natural log of the voltage over V naught, we see that the straight line or linear distribution of the graph, for my specific case, has produced a slope of negative 0.172, in which we will be important in our very calculation. When we divide this value into 1, or 1 over negative 0.172, we get 5.83, which is very close to the value we receive at the RC unit, which is 6, or 30 ohms times 0.2. Finally, getting to the what-if questions of the lab, if we were to use an actual ammeter opposed to our simulated model, or CCK, I believe that we would influence our output by making it slightly lower. My reasoning for this is that compared to our simulation where we can truly set this resistance to zero, it is impossible to do that in the real world with the modern technology we have. All ammeters and all sorts of batteries, as well as other electronic devices, all innately have some sort of resistance. Thus, when we test the circuits, the values we get for the current are going to be slightly lower, exactly by that amount of innate resistance. For the second what-if question, if we were to charge a capacitor with no resistor in the entire circuit, the speed to which it is maximally charged, or potential difference is created in the capacitor, would be incredibly fast, or more specifically, as fast as it possibly could to the absolute zero resistance. That's all for today. Thank you.